Swayam Prabha. Digital India. Educated India.
Now we will go to discuss the linear mapping. Consider two real vectors v and w. A mapping means a map f such that or phi such that v maps to w. It means domain to codomain, and then we have to check it out whether the structure of the vector space preserves the linear or not, that we have to check it out. So, the rule is you take element x comma y under phi, then it will go to phi of x and phi of y, and then check it out if we add the phi of x plus y equal to phi of x plus phi of y, then it is to be what, summation of this, and you take a vector and multiply with the scalar, then scalar into phi of x. So, for all x comma y in V and lambda in R, we can summarize this following definition, call it as a linear mapping, right. So, the linear for the vectors v comma w, a mapping phi such that v maps to w is called a linear mapping or vector space homomorphism. Then it is said to be vector space linear transformation or vector space homomorphism for all x comma y in V, lambda comma psi in R, then phi of lambda x plus psi y equal to lambda into phi of x plus psi of phi of y. So, this is called as a vector homomorphism from domain to codomain. Next definition, injective, surjective and bijective. It is most important that you have to check it out the mapping from domain to codomain. So, consider the mapping phi from domain to codomain v to w, where v to w can be arbitrary sets. Then phi is called injective if for all x comma y in V, phi of x equal to phi of y implies x equal to y, and if it is surjective if phi of v equal to w, and bijective if it is injective as well as surjective. So, injective means every element in codomain must have a unique element from domain to codomain or distinct element in the domain, distinct element or x comma x not equal to y implies f of x not equal to f of y. So, different way we can do that, either this or that, and every element in codomain must have at least one unique image in, at least one image in domain, then it is said to be surjective. Bijective means it is both one to one as well as on to. So, one to one is injective, on to is a surjective, bijective means both one to one as well as on to. With this definition, we introduce the following special cases of linear mapping between the vectors from domain to codomain, and if you say it is isomorphism, then it should follow the linear and bijective, and if it is say endomorphism, then it is what, v to v, domain also same vector and codomain also same vector, then it is to be linear. If you say it is automorphism, then domain and codomain having both one to one and as well as on to and follows with a linear. So, we have a identity definition ID, P means what domain 1, codomain also 1, 2 mean 2, like that same element reflected from domain to codomain, then it is to be identity mapping or identity automorphism. So, keep it in mind the definition so that we can understand the beauty of the linear mapping or linear transformation in terms of the vector spaces, we can do that. Now, let us go with the discussion of homomorphism. So, the mapping phi such that R square in C, R square maps to C mean R square is a 2 tuple from domain to codomain of real numbers, and it goes to the codomain is a complex number. So, complex number is phi of x equal to x1 plus ix2. Imaginary is also associated, is a homomorphism. Okay. Now, you take a phi of x1 comma x2 plus y1 y2, then real part x1 plus y1 add and imaginary part x2 plus y2 add and into I. Therefore, x1 plus ix2 and y1 plus y2, that is the meaning of what? The mapping from domain to codomain. Similarly, we can split it into phi of x1 x2 combined together plus phi of y1 y2 combined together, so that the mapping will be corresponding expression to the mapping, we can write it. Similarly, we can go for phi into lambda of x1 x2 equal to lambda into x1 plus lambda I into x2, then lambda of x1 plus ix2 equal to lambda of phi of x1 x2. Therefore, we can draw in the picture like E1 and E2 and it goes to a vector x, and similarly if it has a complex B1 B2, we have a x vector like that. So, this is a representation of Cartesian form from the mapping to the equations and expression in the mapping. That is a pictorial representation. Now, if phi such that V maps to W and psi such that V maps to W are linear, then phi plus psi and lambda psi, lambda phi and lambda in R are linear too. So, this is the mapping from domain to codomain. Now, we have a definition. Consider a vector V and an ordered basis B1, B2 and so on Bn of V. For x in V, we obtain a unique representation linear combination x equal to alpha 1 B1 and so on alpha n Bn of x with respect to B. Then all scalars A1, A2 are coordinates of x with respect to B, and the vector alpha equal to alpha 1, alpha 2 and so on alpha n r power n is the coordinate vector and the representation of x with respect to the ordered basis B. Now, we have a example, right. Let us look geometric vectors x in R square. R square means 2 tuple with the coordinate 2, 3, that is x can be written as 2e1 plus 3e2 with respect to the basis e1, e2. This means we can write x equal to 2e1 plus 3e2. However, we do not have to choose the standard basis to represent this vector. If you use the basic vectors, basis vector b1 equal to 1 comma minus 1 and b2 is 1 comma 1, we will obtain the coordinate half into minus 1 comma 5 to represent the same vector with respect to b1, b2, and see the picture of a different coordinate representation of a vector x depending on the choice of the basis. For note, for an n dimensional vector space V and ordered basis B of V, the mapping phi such that r power n to V, where phi of ei equal to bi, where I equal to 1 to n is a linear, and because according to the theorem of an isomorphism where E1, E2 are the standard basis of r power n. Now, we have a transformation matrix. Consider the vector space V comma W with corresponding ordered basis B equal to B1, B2 and so on Bn, and C equal to C1, C2 and so on Cm. Moreover, we consider the linear mapping phi such that V to W for j varies from 1 to n, and phi of Bj equal to alpha 1 j C1 and so on alpha mj Cm, which is equal to summation I equal to 1 to m alpha ij Ci is a unique representation of phi of Bj with respect to C. Then we call M cross n matrix as a phi whose elements are given by a phi of I comma j equal to alpha ij. This transformation of matrix of phi with respect to the order of the basis of B of V and C of W. Now, we have a transformation matrix. Consider that homomorphism phi such that V to W and the order basis B equal to B1, B2 and so on B3 of V, and C equal to C1, C2 and so on C4 of V W with phi of B1 equal to C1 minus C2 plus 3C3 minus C4, and phi of B2 equal to 2C1 plus C2 plus 7C3 plus 2C4, phi of B3 equal to 3C2 plus C3 plus 4C4. Now, the transformation matrix A phi with respect to B and C satisfy phi of Bk equal to summation I equal to 1 to k alpha I k C I for k equal to 1 to 3, and is given by A phi equal to alpha 1, alpha 2, alpha 3. We have a representation of matrix, that is phi of B1 corresponding entry 1, 2, 0, right, and then we have a minus 1, 1, 3 and 3, 7, 1, and then minus 1, 2 and then 4. So, coefficient of C1, C2, C3 of the respective equation from 2.95. So, where alpha j, where j varies from 1, 2, 3, and the coordinate vector of phi of Bj with respect to C. Now, we have an example of a linear transformation of the vectors, 3 examples of linear transformation of the vectors shown in the dots. In A is called it as original data, and then we have to rotate with 45 degree, and then we stretch along the horizontal axis, and then general linear mapping will come like this. Now, these are the representation of corresponding matrices, and we consider the 3 linear transformation of set of vectors R square with transform the matrices. Suppose if you rotate 45 degree, cos 45 is what correspond, cos pi by 4 you take it, sorry, cos 45, correct, cos 45, cos pi by 4 you take it, and then minus sin pi by 4, and then sin pi by 4, cos pi by 4. Then corresponding A2 you have a matrix 2, 0, 0, 1, A3 is 1 by 2, 3, minus 1, 1, minus 1. So, this set of matrices we have to transform one to another. Now, in the following we will have a closer look at how the transformation matrix of a linear mapping from V to W change. If we change the basis in V and W, consider 2 ordered bases B1 equal to B B1, B2 and so on Bn, and B tilde equal to B1 tilde and so on Bn tilde of V, and 2 ordered bases C equal to C1, C2 and so on Cm, where C tilde is C1 tilde and so on Cm tilde of W. Moreover, A phi belongs to R power m cross n is the transformation matrix of the linear mapping from V to W with respect to the basis B and C, and A phi belongs to R power m cross n is the corresponding transformation mapping with respect to B and C. And the following we will investigate how A and A tilde are related, and how or whether we can transform A phi into A phi tilde, and if you choose to perform a basis change from B C to B tilde and C tilde. So, this type of the transformation we can do from domain to codomain, or one mapping to the another. Now, consider an example of a basis change, the transformation matrix A equal to 2, 1, 1, 2 with respect to the canonical basis in R square. If we define a new basis B equal to 1, 1, 1, minus 1, then we obtain a diagonal transformation matrix A tilde equal to 3, 0, 0, 1 with respect to B. So, which is easier to work with than A. Now, we have a theorem basis change for a linear mapping phi such that V to W be the ordered basis, where B equal to B1, B2 and so on Bn, and B tilde equal to B1 tilde and so on Bn tilde of V, and C equal to C1 and so on Cm, C tilde equal to C1 tilde and so on Cm tilde of W, and a transformation matrix A phi of phi with respect to B and C. Then the corresponding transformation matrix A phi with respect to the basis B tilde and C tilde is given by A phi tilde equal to T transpose A phi S. So, here S in R power n cross n is the transformation matrix of identity matrix that maps the coordinates with respect to p tilde onto the coordinates with respect to b, and T belongs to R power m cross n is the transformation matrix, and identity matrix is that maps the coordinates with respect to C tilde onto the coordinate with respect to C. Now, we have a definition of equivalence. Two matrices A and A tilde in m cross n are equivalent if there exists a regular matrix S in R power n cross n and T in R power m cross m such that A tilde is T inverse AS satisfy the condition, then it is said to be equivalence. And two matrices are said to be similarity, then A and A tilde belongs to R power n cross n are similar if there exists a regular matrix S belongs to R power n cross n with A tilde equal to S inverse AS. Now, we have an example basis change. Consider the linear mapping phi such that R cube to R power 4 whose transformation matrix is A phi equal to 1 2 0 minus 1 1 3 3 7 1 minus 1 2 4, and with respect to the standard basis we have B equal to 1 0 0 0 1 0 0 0 1 and C equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So, that is the basis we can get it from the transformation. Now, we seek the transformation of A phi of phi with respect to the new basis B equal to 1 1 0 0 1 1 1 0 0 and C tilde is equal to 1 1 0 0 1 0 1 0 0 1 1 0 1 0 0 1. Now, we have a S matrix like this and T matrix is like this, where ith column of S is the coordinate representation and Bi tilde in terms of the basis vector of B. Since B is the standard basis, the coordinate representation is straightforward to find. For a general basis B, we would need to solve the linear equation system to find a lambda I such that summation I equal to 1 to 3 lambda I Bi equal to Bj, where j equal to 1 to 3. Similarly, the jth column of T is the coordinate representation of Cj in terms of the basis vector of C. Therefore, we obtain A phi tilde equal to T inverse A phi S, which is equal to half into the matrix of what T inverse A phi S already found out, substitute it and simply product them. So, this is 4 cross 4, this is 4 cross 4 rows and 3 columns, therefore, 4 rows and 3 columns will come. So, simple multiplication matrix you do that, so that we can obtain the basis vector of this will come. Next, we have to go to discuss the image and kernel. For V such that V to W, we define a kernel or null space if kernel of phi mean phi inverse of 0, 0 mean identity element, means V in vector V and phi of V equal to what? 0 identity element, and image mean, so image of phi equal to phi of phi, which is W in W such that P of phi equal to W. So, this is the meaning of what? Image and kernel. We also call V and W is a domain and codomain of V respectively. Consider the mapping phi such that V to W, where V comma W are the vector space. It always holds that phi of 0 is equal to 0 and 0 belongs to kernel, and in particular the null space is never empty. Therefore, image of phi is a subset of W and kernel of phi is a subset of V is a subspace of V. So, this is a what a picture representation of this. So, if you take a point from the domain, so this is the domain V and W and then 0, and if you take the kernel and then it goes to 0, and if you take the elements from the domain and it goes to image. So, this is the picture representation from domain to codomain of previous definition, what previous slide what we discussed the kernel and images. So, it means if it is a injective mean it is 1 to 1, 1 to 1 mean if x equal to phi of x equal to phi of y, right, phi of x equal to phi of y implies x equal to y, or x not equal to y implies phi of x not equal to phi of y. So, this is the meaning of what representation of injective. So, it means here kernel of phi is equal to identity which is 0. Now, we have to go to the note null space and column space. Let us consider A belongs to R power m cross n and a linear mapping phi such that R power n to R power m where x maps to Ax. For A equal to 1, A1, A2 and so on, An where A are the columns of A, we obtain image of phi equal to A of x where x belongs to R power n and which is equal to summation I equal to 1 to n xi ai where x1, x2 and so on xn in R, and that will be span A1, A2 and so on an subset of R power m. So, means the image is the span of the column of A, also called the column space. Therefore, the column space is a subspace of R power m where m is the height of the matrix. Therefore, the rank of A equal to dimension of image of phi. Therefore, the kernel or null space of a curve phi is the general solution to the homogeneous system of linear equation Ax equal to 0 and capture all possible linear combination of the elements in R power n that produce 0 belongs to R power n. Therefore, the kernel is a subspace of R power n where n is the width of the matrix and the kernel focus on the relationship among the columns, and we can use it to determine whether or how we can express a column as a linear combination of other columns. So, that is the things we have to make a note from the null space and column space. Now, we have to discuss one example, image and kernel of a linear mapping. The mapping phi is such that R power 4 to R square mean 4 tuple to 2 tuple. So, x1, x2, x3 are the what 4 tuple and it maps to what this 4, that is 4 2 rows and 4 column and 4 rows and 1 column, 2 rows and 4 columns and 4 rows into 1 column. So, we have 2 rows into 1 column. So, if you multiply like that, then we have what first x1 plus 2x2 minus x3 and the next one is x1 plus x4. So, what happened? Collect all x1, x2, x3, x4 so that we have a what expression linear combination. So, if it comes like that, then it is said to be linear. If you determine the image phi, we can take the span of the column of the transformation matrix and obtain image phi equal to span of 1 1 2 0 minus 1 0 0 1. So, this is what a span we can corresponding to the matrix. So, we can express what is the meaning of image and kernel and corresponding linear mapping. So, to compute the kernel and null space of phi, we need to solve Ax equal to 0, that is we need to solve the homogeneous equation. To do this, we use the Gauss elimination transformation A into the reduced row echelon form where 1 2 minus 1 0 1 0 0 1 after row reduced matrix make this entry to 1 and this make entry to 0. So, that 1 0 0 1 0 1 minus 1 minus of will come. So, this matrix is in reduced row echelon form and we can use the minus 1 trick to compute the basis of the kernel. Alternatively, we can express non-pivot column as a linear combination of the pivot column, that is column 1 and 2, and the third column A3 is equivalent to minus of times the second column A2. Therefore, 0 equal to A3 plus of A2. In the same way, we see that A4 equal to A1 minus 1 by 2 into A2 Therefore, 0 equal to A1 minus half into A2 minus A4. So, overall this gives the kernel of the null space of S. Therefore, ker phi equal to span of 0 1 by 2 1 0 and minus 1 1 by 2 0 1. So, this way we can find out the kernel of the phi. Next theorem, rank and nullity theorem. So, we have to understand the statement of the theorem for vector space V, W and a linear mapping phi such that V to W, it holds that dimension of ker phi plus dimension of image phi equal to dimension of V. So, if dimension of image phi is less than dimension of V, then ker phi is non-trivial. So, the kernel contains more than identity 0 and dimension of ker phi is greater than or equal to 1. So, this is the information we have to learn from the equation 2.129. And number 2, if A phi is a transformation matrix of phi with respect to an ordered basis and dimension of image phi is less than dimension of V, then the system of linear equation A phi x equal to 0 has infinitely many solutions. And next, if dimension of V equal to dimension of W, then the three-way equivalence phi is injective, if and only phi is surjective, if and only phi is bijective holds. Therefore, image of phi is a subset of W. So, this way we can express what rank T and nullity and then corresponding a relationship between the dimension as well as image and ker. So, these things are remember, then we can understand the beauty of the relationship between the vector space in terms of the mapping and linear mapping and how to convert the corresponding matrices, and we can check it out what all the orders, rank, linear independent, dependent and so on. Thank you.